Hello, and welcome to the next part of the algorithm section. Yes, I'm still excited despite the next topic, which is probably my least favorite. You see, in the past, when I learned about sorting, it involved a lot of math, a lot of different algorithms, and I just never really enjoyed it because I didn't understand why we needed to know sorting. I mean, you just have a sort function usually in a programming language, and that's it, right? I just never understood the point of it. And you're probably thinking the same thing. All right, Andre, there's nothing to learn here. I'm going to skip over these sections. Great lesson. See you later, right? Well, not really. Let me explain. In an interview, sorting is really important. You hear questions like, take an array of numbers and sort them, or the interviewer wants you to do something to some input, and they tell you that this input is sorted. And you're wondering, why did they just tell us that? Why does it matter if it's sorted or not? And why do companies care so much about sorting if I can just use the built-in sort method in my own language? Well, here's the thing. Sorting is not a big deal when it comes to small input data. You'd be right. You can just do something like this. We'd have an array of letters, and this array simply has A, D, say Z, let's add a few more E, R, and finally B. And if somebody asks us to sort this, well, we can just use something like a sort method that comes with most languages. And if I run this, look at that. Nice and easy, just sorted everything. I'm a genius, right? Why would companies ever ask such a simple question of us? You see, the problem is when inputs get larger and larger. Kind of like when we talked about Big O. We don't care about small inputs. That's easy to do, especially with our modern fast computers. It starts costing companies a lot of money when we have to perform operations on larger and larger data sets. That's when things become a little bit crazy and expensive. For example, Google has a ton of websites that are indexed. What if they need to sort those websites in a way? Perhaps sorting a news article based on the time that it was released. And because we're talking about Google here, we're not talking about 10 articles. We're talking about thousands, millions more articles sorted based on date. What about Amazon? Amazon is all about sorting. They sort their products based on category, based on price, based on rating, and they have millions of products. What about Apple? Well, Apple has the Apple Store, and they list all their apps in some form of a sorted order. Podcasts in a sorted order. What about Microsoft? Well, Microsoft, they need to sort all their logs of, let's say, their data centers around the world so that if an incident happens, they know where it's coming from. And then Netflix? Well, they need to sort their shows, their movies, their TV shows somehow, right? And they can't usually just use a built-in sort method that comes with the language. And they usually need custom sorted methods based on the data so that they can lower their costs and lower the operations that their computers need to do. Most places sort their data or pre-process it. And all these companies, including small ones, usually sort data to make sure that it's meaningful. If it's random data that is not sorted, it's really, really hard to access. So most of the time, we sort data or pre-process it. Now, the examples that I just talked about, they are a little bit silly, but it does prove my point. For these companies, if they do something wrong or they do it in an inefficient way, it means losing a lot of money. That's why they ask these questions in an interview. They want to make sure you understand how important the topic is and that you can make the right decision as their employee. What sorting algorithm should you use based on the problem? So that's the goal of this section. I'm going to show you how to implement sorting on your own if you want. But most importantly, we're going to talk about the different sorting algorithms available to you and how you can make the right decisions for your company. And obviously, to ace that coding interview. Now, the reason that most sorting algorithm lessons get really boring is that there's so many sorting algorithms. If we search sorting algorithms on Wikipedia, you get a pretty large list. And implementing these sorts one by one yourself takes a lot of time. But most likely, you will never implement your own sorting algorithm in your life, except for maybe a simple one in an interview. Because most of these, especially the advanced ones that are really fast, are done by academics that spend years figuring out what the best, most optimal way of sorting is. And interviewers don't expect you to be able to implement every single sorting algorithm. My goal in this section is to teach you the high level, what you need to know to become a better engineer and also ace the coding interview. I'll show you how to implement some of the important sorting algorithms, but more importantly, we're going to talk about the trade-offs between them so that you're able to talk about them intelligently during an interview. For the next few videos, we're going to talk about these sorting algorithms and also a couple of bonus ones towards the end. But the key thing to remember is that as more and more data is handled by our computers, which is a big trend in computing, sorting and searching are two of the biggest computer science problems in the software world. Searching we're going to get into in the next section, but sorting is something we'll hopefully master at the end of these videos. So let's go learn how to make good decisions when it comes to sorting. Welcome back. Let's talk about sorting when it comes to specific languages. And I'm going to use JavaScript here. I'm going to be showing you different sorting algorithms that can be used with any type of data. It doesn't just have to be strings, doesn't just have to be numbers, it can be any type of data. But I also want to show you why sometimes you want to be careful when it comes to sorting. And just don't trust that your built-in method in your own language sorts data correctly. Let me demonstrate this with JavaScript. Let's say we have another array here, and this array, we'll call it basket. And this basket will have, instead of letters, we'll have some numbers. We'll have 2, 65, 34, 2, 1, and let's say 7, and one more 8. Now, we saw that when we sorted the letters, everything looked good. What happens if I sort the basket here of numbers? What do you think will happen? And I encourage you to try this with your own language as well, and see what kind of results you get. Let me click Run here. That's the result. Is that what you expected? That doesn't look sorted, does it? Now, this is a silly example, but it's important to demonstrate that when it comes to sorting, you want to make sure if you're not implementing it, you know how it works. For example, when it comes to JavaScript, the way it sorts numbers is that it actually converts them to string. At least that's how the sort method works. So what happens underneath the hood is instead of just comparing numbers, it does something along the lines of if it gets to 65, and then it's going to grab the character code in the first index. So we can use the method char code at and give it 0. So it's going to measure the character code at 65. If I run this, I get 54. Now, 54 is Unicode. And if I go to Unicode table, this is how characters are encoded in our computers. Now, if I go to 6, I see that, we see when we hover over that, it says the HTML code for it is 54. The character representation is 54. So that's what's happening here. If I do, let's say 2 here, and we'll do one more 34. And let's just console.log these so we know what's happening. And I click run. We see that 2 is 50, 65 or 6 is 54, and 34 is 51. But if I do something like 7, it's going to grab the number and it's going to be 55. So a lot of people get confused when they use a sort method like this and they don't get the response that they wanted. And that's why it's good to read the documentation of whatever you're using, such as a sort method, and understand how it works in a language. And to add even more confusion, you see here that the time and space complexity of sort cannot be guaranteed, as it is implementation dependent. Remember, JavaScript has a standard called ECMAScript. A governing body suggests what it should look like. However, how you implement it is really dependent on different engines. So the Chrome browser would use a different JavaScript implementation than, let's say, Firefox or Safari. And what kind of sort algorithm they use underneath the hood is dependent on the browser. And that's something we're actually going to talk about later on in the videos. But to finish off this section about the weirdness of sorting, let me show you one more example. Let's say I have an array of Spanish words here. Único, árbol, cosas, fútbol. And we want to sort these. What do you think will happen? Let me remove this and do this here. If I click run, I guess cosas, fútbol, árbol, único. Again, because of the Unicode characters, the A with the accent on it is not the actual A that would come before something like C, as you can see here. So in this case, to solve this problem, we would have to do something along the lines of creating a function inside of sort that takes A and B, which is the first and second item, and it's going to return A plus locale compare B, which allows us to compare these even if there were different languages. So if I run this, you see that it's now fixed and everything is working. And again, locale compare is something that you can check out and I will link to over here. Now, the reason I'm showing you this is not because we want to become JavaScript experts. Well, everybody has their own language, but to show you that there's many ways that we can sort things. And even with small little differences like this one, there's a lot of considerations that need to be had. And underneath this sort method is actually one of the algorithms that we're going to learn about in this course. And I also recommend you checking out the MDM page, which I'll link to, that shows you how you can compare different things, such as numbers, such as objects and items in an object, using the sort method. You see, in order to sort this properly, we'd have to do something like this, where we have a function inside of the sort method that will take A and B, which is the first and second item, and we'll simply say return A minus B. And if we run this, we see that our numbers are now sorted. But that's enough for now. Let's talk about the sorting algorithms that are being used in computer science in the next video. I'll see you in that one. Bye-bye. Welcome back. You see in our mind map here that we're now in the sorting section. And this big O of n log n, something we haven't talked about, is showing up. We'll get to that in this section. But I want to add a quick note here. Looking at all these sorting algorithms, and there's a lot more. It's important to note that you don't need to write a sorting algorithm from scratch, most likely ever in your career. Frameworks usually do that for us. But you do, however, need to know how they work because, well, one, you're most likely going to get asked in an interview, and two, because it makes you a better engineer. But this section is also about being efficient. You see, you can spend a lot of time on each one of these sections implementing your own and talking about it deeply. Because I don't think I've ever heard of anybody actually having to implement in code manually these sorting algorithms. Most of the time, you can just talk about it, or the interviewer tells you that the array is sorted and you need to know what to do with it. But implementing it from scratch, that doesn't really happen. But I've included it in this section because it's good to know how they work. And I'm not going to lie. Coding sorting algorithms is not my favorite either. Don't let that deter you. I encourage you to watch the next couple of videos and even practice coding your own sorting algorithms because it will help your learning. But the main thing that we're going to get from this section is not how to implement these. I mean, we will do that, but the key is the trade-off. You see, we have the big O cheat sheet here that we definitely know about, right? We talked about data structures and how there's trade-offs. Well, when it comes to sorting, there's trade-offs as well. You see how there's some time complexity trade-offs, space complexity trade-offs. And it's important to know when to use what algorithm. That's our goal of this section. And before we get into our first sorting algorithm, I want to show you this nifty little tool that I'm going to link to. We have a few sorting algorithms. We have insertion sort, selection sort, bubble sort, shell, merge, heap, and then 2 different variations of quick sort. And we also have different data sets. This is a random data set. See how they perform when I click here based on different sorting algorithm. See that they're all working and all of them finish at different times. One is a lot slower than the other. What about nearly sorted? Again, one, such as insertion sort, is really, really fast while others are slower. Reversed, if the items are reversed and we need to sort a completely reversed list, again, different algorithms perform differently. It's never one that wins out over the other. Depending on the inputs, what we need to do, they're different abilities. Let's start to learn about these different types of sorting algorithms so that by the end of these videos, we can make the right decision when to use what. I'll see you in the next one. Bye-bye. Welcome back. Let's start off with the very first item on our list, bubble sort. Sounds kind of playful and nice, right? Bubble sort is part of these first 3 sorting algorithms here. that are called elementary sorts. They're very simple, basic sorting algorithms that you would usually think of if somebody asked you to sort something at the top of your head. The second items here that we're going to get into later, merge sort and quick sort, are more complex algorithms that most of the time can be more efficient than the first ones. But to build that Lego block, let's start off with bubble sort. How does bubble sort work? Well, let me ask you a question. If I gave you a list and I asked you to sort it, in your head, imagining that you had blocks of these letters, how would you move them around? Or how would you tell a computer to move them around to sort it? And bubble sort might be one of the first things that comes into mind. You see, bubble sort comes from the idea of bubbling up the largest value using multiple pass-through. Let's see what I mean by that. We look at 6 and 5, and then say 6 is larger than 5. And then we look at 6 and 3, and say 6 is larger than 3, let's swap them out. Then we look at 6 and 1, and once again, 6 is larger than 1, let's swap them out. We look at 6 and 8. 8 is larger than 6, so keep it the way it is, and let's move on to the next one. 8 and 7, let's swap them out. 8 is larger than 7. 8 and 2, swap them out. 8 and 4, swap them out. We bubble up the highest number, and then we go from the beginning. 5 and 3, 5 and 1, we bubble up the largest number, so that 7 comes next. Then we keep going until 6 comes next. Then we keep looping until we bubble up the highest number one by one, until we have a sorted list. That is bubble sort. Now, before we even code this, what do you think of bubble sort? As you might have guessed, it's not the most efficient, is it? Look at how many comparisons we did, and everything was one by one, looping and looping and looping. And bubble sort is one of the simplest sorting algorithm, but also one of the least efficient. So don't hate me for showing you how this works. It's usually used as a learning tool as the first step in learning a sorting algorithm. What do you think the time complexity and space complexity of this algorithm is? The answer? Well, we can just use the big O cheat sheet. If we look at bubble sort, we see that the cases that we're most interested in is the average and worst case. We see that it's O of n squared with a space complexity of O of 1. We're not really creating any new data structures. We're just comparing items in nested loops one by one. But let's see it in code to see why this is O of n squared. And I want to challenge you here. In the next video, we're going to code along the bubble sort algorithm. But if you want, go ahead and try implementing this on your own and see how your code matches up with mine in the next video. I'll see you in that one. Bye-bye. Welcome back. Let's code our own bubble sort algorithm. I'm going to create a function called bubble sort. That's going to take in an array. And I have an array up here for us of these numbers. And ideally, when we enter this array into this function, it spits out a sorted array. And based on the animation that we saw, we ideally start from the beginning, compare first and second item, swap out the items if the left one is larger than the right, and keep going until the largest item ends up in the last index, and then we loop over things again. The first thing I want to do is say that I'll just create a variable so I don't have to keep repeating myself. I'll get array.length here, which will be the length of this item, which should be 10, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Never mind, it's 11. And in here, we'll do a for loop. And we'll say let I equals to 0, which will be the first index of the array. I is less than length. I plus plus. And within here, we grab the first item. We now want to compare it to 44, and so on and so forth. We should know this by now. We want to add another for loop. J is going to equal 0. J is going to be less than length. And we'll say J plus plus. Now in here, we'll say that if array J at index of 0, so that is 99, is greater than array J plus 1, that is 44. So if 99 is greater than 44, in the first loop, we'll say, let's swap numbers. So we can simply do that by saying, creating a temporary variable that holds array at J which the first pass, it'll be 99, and give the first index of 0 to array j plus 44, or plus 1, which is 44. And 99 now goes into the second index, so that means array j plus 1 is going to equal array j. You might need to pause the video to really understand this, but all we're doing is just swapping numbers if the left-hand side is bigger than the right-hand side. And once that is done, we increment j to 1 so that we compare index of 1 and 2, and then we compare index of 2 and 3, 3 and 4, 4 and 5, until we bubble things up, and then we go to the top and compare the items again in the outer for loop. Let's see if this works. Oh, and I just realized this array j should be temp here. So remember 99, we placed it into a temporary variable and assigning it to the index to the right. So if we run bubble sort now, we'll say numbers and we'll console log numbers to see if it's sorted. If I hit run, oh, console log numbers, make sure I can spell. Let's hit run. And look at that. Our list is now sorted. That was bubble sort. And as you can hear, we have two nested for loops giving us O of n squared, but we're not really holding variables to another data structure or holding the numbers into other data structures. So the space complexity is O of 1. As we can see in our big O cheat sheet, bubble sort is probably not the best algorithm, although it has good space complexity. You can use the code that I'll leave for you in this lesson to play around with. But for now, let's go on to our next sorting algorithm. Congratulations, you've just completed your first sorting algorithm, but we have more to go. So let's go to the next one. Welcome back. Let's talk about our second sorting algorithm, and it's called selection sort. Now, selection sort is, again, one of the simpler possible ways to sort a list. And the algorithm works by scanning a list of items for the smallest element, and then swapping that element for the one in the first position. Let me show you with this animation here. We started with the first item and then the second item. The red here signifies that it's the smallest item that it's seen, and the blue is scanning ahead to find the smallest item. So right now 8 is the smallest item, but we encounter 5, so 5 switches to the smallest item. We encounter 2, so 2 becomes the smallest item. We keep going, 6 is not smaller than 2, 9 isn't, 3 isn't, we encounter 1, 1 becomes the smallest item. We keep going, we find 0, so 0 becomes the smallest item, and we've just finished the list. So now we move 0 to the first index in our list. So we swap it out, and then we keep going back to the beginning, finding the smallest item through the list, which is 1, and then placing that in the second index. And we keep going like this until we find the smallest item, place it next in the list, next in the list, next in the list, until we have our list completely sorted. As you can see, with selection sort, we're still going to see a time complexity of O of n squared. If we look at the time complexity chart, we see that selection sort is not very fast, similar to bubble sort. We have those nested for loops, but uses a space complexity of O of 1. It doesn't really add any additional data besides the input. Now, using the animation that you just saw, can you implement your own selection sort? I'm going to leave this for you as an exercise, using what you know from the bubble sort and what you just saw for selection sort, how you can use that information to sort the list using this algorithm. And I'll show you the solution in the next video. Bye-bye. Welcome back. I've left for you the solution for the selection sort. Now, I'm not going to be going one by one through each sorting algorithm because it does take a lot of time. I don't want to bore you and lose you because there's so many more exciting things happening throughout the next couple of videos. So I'll leave this for you to see how it works. It's not that much different from bubble sort. We see that with selection sort, we're setting the current index as the minimum. So the very first item in the array becomes the minimum. But when we loop through the rest of the list, we want to update the minimum if the current is lower than what we had previously. So what we had here, where we initially set the first item in the array, 99 as the minimum. As soon as we get to 44, we're going to say, oh, 44 is less than 99. Let's update the minimum so that index where 44 is now the minimum. And we're going to swap out those numbers, just like we saw in the animation. And it also is a really well-documented thing on the internet. For example, if you are a Python developer, you can just type in Python selection sort, and you'll find that, yeah, you can find how selection sorts. It's implemented in Python, and you can run the program as well. So depending on your language, you can usually click on the first or second link and show you how the algorithm is implemented. As you can see here, we have 2 nested for loops looping through the entire array, so it's O of n squared. For the rest of the sorting algorithms, I will have the code provided for you, so you can play with it and interact with it. You see that the sorting works as expected, but you can also search for your own language to find the sorting algorithm so you understand it on a deeper level. Let's talk about the next sorting algorithm in the video coming up. Welcome back. I want to show you the greatest thing ever in computer science, especially when it comes to algorithms. I'm going to link to this channel because I just think is the greatest thing ever. Also, the comments are absolutely hilarious if you're nerdy like me. But somebody created a sort algorithm dance playlist where they take different sorting algorithms and show them how they work with some traditional music. Let's say traditional Romanian music, traditional Hungarian music, traditional Transylvanian Saxon folk dance. And they show different sorts. So you can check out bubble sort, which we've talked about, or selection sort, which we're doing right now, to help you with your exercise and to write your own algorithms for the exercises. Not only is the music just absolutely amazing, it really, really helps you with how sorting algorithms work. By the way, my favorite one is the quicksort one, which we're going to get into. It's the best dance to see, especially if you do it at 2x speed. 2x speed, these dances become really, really fun to watch and really help you out. Anyway, this is a little fun thing to do with your exercises when you're trying to figure out how to write and implement your own sorting algorithms. I think this is the best way to visualize things to show you how they work. Welcome back. Up until this point, we've talked about sorting algorithms that weren't very efficient and aren't that commonly used. Now, insertion sort is not the most efficient algorithm either, but there's cases where it's actually extremely fast, which we're going to talk about. So pay attention because this one starts to get important. You see, insertion sort is useful for times when you're pretty sure the list is almost sorted or it's already sorted, which sounds silly, but sometimes this is important in computer science. And in a best case scenario, you can get O of n, or linear time, when the list is almost sorted. Let's see how it works. We have a list and we look at 6. We look at the first item and just leave it where it is. We now look at the next item, 5. And because 5 is less than 6, we switch it over. And then we go next into the list. We say, hey, 3, where are you in relation to 5 and 6? Well, it's less than those two, so we shift those over and 3 gets placed in the front. So we now have this list of 3, 5, 6. We look at 1 and say, oh yeah, that's the first item. We want to shift everything, put 1 to the left. We then look at 8. Well, 8 is larger than all those items, so let's just attach it to the end of that list. 7, well, goes between 6 and 8, so place it in there. 2, between 1 and 3, place it in there. And 4, place it between 5, or 3 and 5. And that's it. This is probably the way that your brain works if you physically had Lego blocks with these numbers and you would move things around. And this type of sorting performs really, really well when it comes to small data sets, which we'll get into later on with our exercises. But can you do this type of sorting in code? See if you can implement your own insertion sort. Same thing as before. This time, we have the insertion sort algorithm. Based on the video and the YouTube dancers that I'll link to, can you implement your own insertion algorithm? In the next video, I'll show you the answer. Welcome back. were you able to figure out insertion sort? I have the answer here for you. Just like it happened in the animation, we first loop over the array, and if the item we're looping for is less than the first item in the array, well, we just move that item, use the unshift method in array, and add it to the first index in the array. Otherwise, if the item we're currently looping over is not less than the first index, in that case, we got to figure out where the number should go. So we're going to loop through things, do an if statement to see where the number should go, and then we move that number to the right spot using the splice method. So that if we click run here, we have our list sorted. I'll once again leave this function here for you to play around with, but I want to quickly talk about the big O complexity of insertion sort. There are times where insertion sort can work really, really well. The best case scenario for insertion sort, when the list is almost sorted or the data is really small, it can be really fast. If we go back to our little animations here, and we look at insertion sort in a nearly sorted data, and I click play, you'll notice that it's the first one that will finish. Quite fast, actually, compared to all the other ones. Let's see that again. You'll see that it's the first one done. Quite fast. And as we'll discuss in the next videos, when it comes to small datasets or datasets that are nearly sorted, you want to use insertion sort over most other sorting algorithms. Well done. Let's move on to the next sorting algorithm. Welcome back. Up until this point, we talked about sorting algorithm, bubble sort, insertion sort, selection sort, that were called elementary sorts. They were okay, but they had those nested for loops, and most of the time, it was O of n squared, which was a little bit slow. Can we do better? Well, yes we can. We're going to encounter our last big O on our list, O of n log n. Now, in order to understand what O of n log n means, we have to talk about our next sorting algorithm, merge sort and quicksort. You see, unlike bubble sort and insertion sort and selection sort, they use the technique that we've heard of before, divide and conquer. We learned about this when learning about trees. Remember, when looking through a phone book, we open up that book not from the first page, but from the middle page, and we keep breaking up the pages until we find the name we're looking for. And merge sort and quicksort use this concept of divide and conquer, and the idea of recursion, which we've talked about, to divide the problem down to do work on each subset, and then combining the solutions. Now, we're going to see how this actually works, but I want to remind you that anytime we see something like divide and conquer, it usually gives you a log of n advantage. And as you can see here, it is the last piece of the puzzle, O of n log n, that actually improves, is better than O of n squared. The next couple of sorting algorithms we're going to look at are not going to have nested for loops and have O of n squared. Instead, they're going to have this time complexity, which makes things a lot better and saves companies a lot of time. In order to understand what this means, we have to start off with looking at merge sort. Let's have a look at how it works, and then I'm going to explain what the benefits are. We have the same list as before. We're going to take this list and actually divide it in half. And then we're going to divide each of these subsets into half again. And then we're going to divide those sublists into half again until we have one item. And once we have that divided up, we're going to take the first item and second item and say, hey, which one should I put first? Let's put 5 first and then 6 right after. And notice here how we're building a reverse tree in a sense. Then we look at 3 and 1 and say 1 and 3. So we're getting closer and closer to that root node. We're comparing 8 and 7. 7 comes before 8. 2 and 4. 2 before 4. And now we again combine those lists in that reverse tree, saying 5 and 1, which one comes first? 1 comes first. And then let's compare 5 and 3. 3 comes first, then 5, then 6. Then we look on the right side. We say 7 and 2. 2 comes before 7. What about 7 and 4? 4 becomes before 7. And because we know that 7 and 8 are already sorted, we just place 7 and 8 right next to each other. And then finally, we combine these last two lists into our root node to combine the list and make it sorted. 1 and 2, 3 and 4, 5, and then 6, 7, and 8. And we have our sorted list. Now, that looked extremely complicated, a lot more complicated than the other sorting algorithms, right? Merge sort is one of the most efficient ways you can sort a list of things, and typically is going to perform better than most other sorting algorithms. And in terms of complexity, well, it's definitely a lot more complex, isn't it? We're using divide and conquer approach, which should tip you off that it's going to use some sort of recursion. The first part of n log n, that is n, comes from the fact that we're still comparing everything. We have to look at each one of the numbers and compare them in order to sort it. Now, once we divide the list into 1, which finding the middle index of these things are actually O of 1, because it's an easy mathematical operation. Get the length of the list and find the middle. But once we divide the array, we need to sort the items, which is going to take O of n. We have to look at every single item and actually sort them. And we're able to create the list. But unlike bubble sort, for example, although we have to compare everything at least once, we don't have to compare everything to everything like we did with bubble sort. All we have to do is compare their local lists to each other. Remember, with something like bubble sort or insertion sort, once we went through the list once, we then compared the next item to the rest of the list. Merge sort is also helpful because it's what we call stable, which just means that if you have equivalent elements, that is, let's say 6 and 6, or a name that is the same, it will keep the original order in the array. And this can sometimes be important depending on the type of data. Let's have a look at its big O. We see that merge sort has O of n log n, with a space complexity of O of n. Unlike bubble sort, insertion sort, and selection sort, we have a bit of a bigger space complexity because we have to hold on to that divided up list in memory. So that is one downside of merge sort. But we've now managed to make our sorting algorithm a lot faster. Now, how do we implement merge sort? I have here for you an exercise. I want to warn you, this is really difficult. Merge sort is really hard to implement and wrap your mind around. If you don't feel comfortable with recursion, it's going to be a little bit tough. Keep in mind that I'm showing you here how to do it just for your own interest. But most likely in an interview, you're never going to be asked to implement your own merge sort. You're just going to be asked maybe how it's implemented. And I've created a little skeleton to help you out here. We have the merge sort that is going to have a function that takes an array. We have the base case, because we're going to use recursion here, saying that when array length is 1, remember, there's only one item in the list. That is, when each one of this is up at the top in its own list, we're going to just return the array. Now, in here, we're going to return, and we're going to merge sort the left-hand side and the right-hand side. And we're going to use this function, merge, that is going to merge the left-hand and the right-hand side. So the first step is for you to split the array down the middle in the left-hand and right-hand side in here, then run it with the merge sort algorithm. And in the merge function, I want you to actually do the comparison. I don't expect you to get this right away. There's very few people that can do this off of the top of their head. But see if you can use all your resources available, our Discord community, or even Google, to figure out how to create your own merge sort algorithm. And I'll see you in the solution video. Bye-bye. How was merge sort? Pretty difficult, right? I have the answer for you here. And I'm not going to code along because, well, this is one of those pieces of code that me just writing in and typing it in a 30-minute video isn't really going to help your understanding. I recommend that you go through this code line by line to fully understand it. But if we take a look here, all we're doing in the first pass in the merge sort function is we're going to get the length of the array, find the middle of the array, and then we're going to slice the array into the left-hand side and the right-hand side. So that if I console log here and I click run, we see that the first time around, we're just splitting the item right down the middle, where we have 99 all the way up to 1 in the left-hand side and 5 to 0 in the right-hand side. In the next pass, because remember, we're doing recursion and this is being called again, when we get to here, we're now dividing up 99 and 44 and 6 to 1 into its own pass, and then 99 and 44 into individual items, 6 and 2, 1 into left and right, until we have everything into one item. And then we start splitting off this hand side as well. Now, what about the merge function? The merge function is going to be a little bit hard to read. But if we take a look here, all we're saying is we have a results array that we're going to fill everything with, and we're going to have a left index and a right index. And we're going to compare here. Is the left index less than the length of the left array and the right index less than their right array length, which makes sure that we have items in our array? If that's the case, then let's compare our left item to the right item and push into a new array, into our results array, the item that is less. In this case, it'll be the left-hand item. And then we increment. Otherwise, if the left item is higher than the right item, we do the opposite, and the right item goes into our results. Remember, this merge function is doing what we saw in the animation. We're splitting the function down in the first part of the function, and then in the merge, we're going to take the left and right, compare it, and place it into the results array. And then go to the next, and keep doing this over and over and creating our results array. If I console log here, left and right, and I click run, we see exactly what we're doing. We have 99 and 44, and then 2 and 1. So on the left-hand side and right-hand side, 99 and 44 get compared, becomes 44 and 99. And then we compare 2 and 1, which becomes 1 and 2. Then 6 and 1 and 2, which becomes 1, 2, 6. And we keep going until the very last step, where we have two lists here. And we compare them, 0 and 1. We place 0 in the results array. And then we place 1, 2, and just keeps going and keeps going. Exactly like our animation. Now I encourage you to play around with this and perhaps go step by step. It is a really hard algorithm to get. The bad news is that the next algorithm is even more complicated. But luckily for you, as I said, you won't have to ever do this in an interview. You just need to know that merge sort is a great algorithm to use because we get O of n log n big O. Let's take a look at another sorting algorithm. Welcome back. Let's talk about our fifth sorting algorithm, quicksort. Even just from the name, you're thinking, this is going to be quick. Quicksort, just like merge sort, is a divide and conquer algorithm, which means, and should ring a bell in your head saying that, there's probably going to be O of n log n. And if you're thinking that, you're right. You see, quicksort uses something called a pivoting technique to break the main list into smaller lists. And these smaller lists use the pivoting technique until they are sorted. But let me show you an animation of quicksort. Quicksort works like this. And if you're looking at this diagram like I am, and you're completely confused as to what is happening, this describes quicksort fairly well. It's pretty complex to understand. So let me show you a better demonstration. I have a little diagram here. Let's say we have a list that looks like this. We have 37895219554. What we do here is we pick a random pivot. Let's say that 4 is going to be our pivot. Once we pick this pivot item, we're going to say, all right, I want all numbers that are less than 4 to come to its left, and all numbers that are greater than 4 to come to its right. So what do? Well, we start comparing the numbers. We look at 3 and 4. All right, 3 is to the left of 4, that's fine. What about 7 and 4? 7 is higher than 4, so it should be to its right. We're going to move 4 to the left position to make space for 7. 7 jumps over to the right, and we swap the 5 that 4 came into the 7th position. And now we check 5 and 4. Oh, we got to do the same thing. We put 5 to the right of 4 and swap 9 in there. Once again, 9 is higher than 4, so 9 comes to the right of 4. Then we look at 8, same thing with 8. And then finally, 5 and 4. Well, 4 and 5 switch places. And now we have a list that has 4 as the pivot, and we know that 4 is going to be in that position in the array. And everything else to the left of it and to the right of it still needs to get sorted, but at least we know where 4 stands. From there, using divide and conquer, we now split the list, and we do the same thing. We get a pivot on the left list, which will be 2, and we say everything to the right of 2 should be higher, everything to the left of 2 should be lower, and we have this left list sorted. On the right, we do the same thing until we split the list with 7 in the middle, and we keep breaking things down like a tree, and this is where divide and conquer comes from, until we have all the individual lists sorted and we combine them. Now, you might have 2 questions for me looking at this. One is, how do we even pick this pivot point? And that is kind of random. It really depends on the situation, but as you see here, we just happen to pick the pivot point as always the last item in the array. The second is, how am I ever going to code this? And this is pretty challenging, and I don't expect you to get it. I'll leave code for you and you can try it out if you want. But the best way to understand quicksort is my favorite Hungarian dance ever. I'm not going to play this for you. You can play it on your own, but I swear I could watch this all day. I think the dancing is awesome, the music is awesome, and well, if you speed it up to 2 times, it's even better. Here in this video, let me mute this. You'll see that this person in the black hat is going to be the pivot, and everybody is comparing, the person in the red hat is the pointer, I guess, or the item that's being compared to the pivot. And you'll see here that as soon as we get to 2, this person is number 3, they're going to say, oop, you should be to the left of me. So they're going to dance. By the way, great dancing moves. I need to learn these steps. And 2 and 3 are now in different locations. And now we compare 0 and 3. Now, this implementation and the visual that I just showed you is a little bit different. But the idea is the same. Quicksort can be implemented in different ways, but the idea of a pivot is the same. I encourage you to watch this video to fully understand how it works underneath the hood. But let's go over the main concepts. Quicksort is really useful. And between quicksort and merge sort, I would say those are the most used sorting algorithms. You'll notice here 2 things. One is that quicksort's space complexity is really good. I mean, not as good as bubble sort or insertion sort or selection sort, but it's still better than merge sort. Its worst case is O of n squared. That is because it can be O of n squared when the pivot is the smallest or the largest item in the list, because then you're not really splitting the list in half. And because of this, you really want to make sure that you pick a good pivot for quicksort. You'll get the better space complexity, but the worst case could be bad. So in those cases, merge sort might be better. If your list was pre-sorted for whatever reason, and in that list, if we pick the pivot to be the first item or the last item, then our sorting routine here would take a very long time. Because again, the list will not really be split in half. And ideally in a quicksort, you're picking the pivot intelligently based on your list. Now, quicksort, there's a lot of variance to it and there's different implementations. But I want you to take this away from this video. Quicksort is usually the fastest on average. But the one downside is that it has some pretty nasty worst case behaviors. So if you have to guarantee no bad data, or you can't guarantee that the pivot's going to be good, then you should be avoiding quicksort. But on average, it's usually the best sorting algorithm. All right, so we've learned 5 different sorting algorithms. But the most important part is, when should I use what? In the next video, we're going to go over exactly that, followed by a fun little exercise. I'll see you in that one. Bye-bye. Welcome back. We've learned our sorting algorithms. But you might be asking yourself, Andre, I'm still kind of confused about when to use what. What about if I get asked in an interview a question about which sorting algorithm will be best if I had a user's data of 100 million names that need to be sorted? Well, let's go over some rules. 1. When should you use insertion sort? Well, insertion sort should be used with only a few items. If your input is small or items are mostly sorted, it's really, really fast. It uses very little space, and most importantly, it's really easy to implement in code. So remember this, only a few items and mostly sorted data, you should use insertion sort. What about bubble sort? To be honest, you're never going to use bubble sort. It's only really used for educational purposes as a way to teach sorting, but it's very rare that you'll find this in real life because it's just not very efficient. What about selection sort? Again, same thing with selection sort. As you can see, its numbers aren't very good, so most likely you won't be using it. Mostly it's being used as a teaching mechanism, which I did. Sorry, didn't mean to waste your time with learning selection sort, but it is important to build the foundation. What about merge sort? And this one's my favorite. Why? Well, merge sort is really, really good because of divide and conquer. We have O of n log n. It's fast, and because best, average, and worst case is always O of n log n, we always divide up the list evenly, you can always guarantee that this is going to be the case, which is not the case for most other algorithms. So if you're worried about worst case scenarios, you should use merge sort. But if you want to sort in memory on your machine and you're worried about space complexity, merge sort is going to be really expensive. It uses space complexity of O of n. However, if you had huge files that can't be sorted in memory, so you have external sorting that you need, maybe like a process outside of memory, it's suitable for external sorting, then merge sort is good because we won't care as much about space complexity then. What about quicksort? Quicksort is actually better than merge sort, right? Average case and space complexity. I mean, it has the same speed as merge sort, but less space complexity. It's probably one of the most popular sorting algorithms. But the one downside is this worst case. If you don't pick the pivot properly, you could have a really, really slow sorting. So you have to be careful. And if you're really worried about worst case, then you'd rather pick something else. Now, you might be asking yourself, Andre, what about heap sort? You haven't really talked about that. I'm going to leave resources for you so you can learn about heap sort as well. It's very similar to quicksort and merge sort, but you see here that it has a space complexity of O of 1. Isn't this better than all of the above? Well, heap sort can sort in place and doesn't have the worst case quadratic behavior that quicksort has or the memory usage that merge sort has. But on average, it's actually slower than quicksort in most cases. It's one of those things where with heap sort, unless you're really, really worried about worst case and memory, then you might use it. But most of the time, I would say you're using quicksort or merge sort. Okay, but you're saying, what about these ones down here? Bucket sort, Radix sort, or Radix sort, and counting sort? How come you're not talking about these ones? Why can't we just use these? They look a lot better than all the other ones, especially when it comes to time complexity. Good question. Let's talk about that in the next video. Welcome back. We've talked about these 5 sorting algorithms. And by now you should know that merge sort and quicksort, although they're harder to implement, are the most often used algorithms in real life because they use divide and conquer to get us this O of n log n performance boost. But can we beat O of n log n? And here's the thing. Mathematically, it is impossible to improve on this. If anybody comes up with an algorithm that is faster than this, they're gonna be very, very rich. Mathematically, it's impossible because O of n log n means that we have to sort by comparison. All of these sorting algorithms have to compare every number to each other. But there is one exception to this rule. You can improve this if you don't make comparisons. Huh? What does that mean? There's a small section of inputs that we can actually beat O of n log n. And these are called non-comparison sorts. And you'll most likely see counting sort and Radix sort. But what does that mean? Counting sort and Radix sort is an entire different way to think about sorting. With comparison sort, we decided the order of the numbers based on asking the question, hey, is this element bigger than the one over there? What about the one over there and over there? And we just kept doing that. Every number got compared to each other. Non-comparison sorting does it a little bit differently. We're going to use the way that numbers and data is stored on our computers in zeros and ones and take advantage of that fact to sort things. Now, this can get pretty complex. And as you can see here in this paper, just looking at the diagrams and, for example, Radix sort here and how we store numbers in zeros and ones, we can use this knowledge to actually sort some things. I'm going to leave resources for you if you want to get really technical and into this topic. I do warn you, it can get a little bit mathy. But the one thing to note here is that these type of sorting algorithm, counting sort and Radix sort, only work with numbers, specifically integers, in a restricted range. So if you have only numbers that you want to sort, and the range of those numbers go from, let's say, 0 to 100, that is a small range, then you would use something like this to make things really fast. But it wouldn't work on any type of data. It only really works on numbers because of the way numbers are stored in memory. You see, unlike something like merge sort or quick sort that are universal, that is, they can sort any type of data, things like counting sort and Radix sort is only useful for fixed length integers. But they are able to beat the speed of O(n) log n. And as you can see here, bucket sort, Radix sort, counting sort, in their average cases, have O of n plus k, O of nk, O of nk. What n and k means is beyond the scope of this course, and some argue that in the end, this actually still turns out to be pretty slow. I'll leave resources for you, like I said, so you can read up on them. But the only thing you need to know about these is that sometimes if you have numbers that are within a certain range, it could be faster than quicksort or merge sort. So now that we know this, let's do some interview exercises based on sorting to solidify what we just learned. Welcome back. I hope your brain is not mush from all these sorting algorithms. I know I keep saying this, but sorting is one of my least favorite topics because there's just so much to learn. And most people focus on just coding sorting algorithms, which just doesn't apply in real life. Most developers and engineers go their entire life not ever coding a sorting algorithm from scratch. But we are going to encounter situations where we need to make decisions on which sorting algorithm to use. So to prepare you for that, I have a couple of questions. And the questions are numbered here. And I want you to answer each question. If this was asked to you by your employer or boss, or maybe an interview, what type of sorting algorithm you'd use based on this factor. For example, we have 10 schools around your house and you want to sort them by distance. What type of sorting algorithm will you use? And you'll see here we have about 8 questions. Give it a try. I'll link to this exercise, and in the next video, I'll give you my opinion. Remember, there's always pros and cons with everything. So really think about this, and I'll see you in the next video. Bye-bye. Welcome back. How was this exercise? Let's go step by step and see how your answers match up. First one, sort 10 schools around your house by distance. So the input is only 10. It's fairly small. We need something simple. In this case, I'll probably use Insertion Sort. It's really fast on small sorts. It's easy to code. And it has space complexity of O of 1. It also could be that these 10 schools are already pre-sorted or are nearly sorted on our list. So insertion is just the simplest for this type of small data. I like insertion sort for this type of things. What about this one? This one's a tough one. eBay sorts listings on their website by the current bid amount. So what would you use for this? Well, for this, I would actually use something like Radix or counting sort. Because, well, a bid is usually a number between, let's say, $1 to, let's say, 50,000. Probably even less when it comes to payment on eBay. Let's say $1 to $100. These are numbers that need to be sorted, right? And because it's a fixed length of integers, integers are most likely not going to be 100 million. Because, well, hopefully nobody's bidding that much on eBay. So I would use Radix or counting sort to beat that O of n log n time, knowing that the bids are always going to be number within a certain range. What about, not sort, sport scores on ESPN? Well, sports scores can vary. There's decimal places sometimes. There's different formats such as tennis and soccer and different things. And there's definitely lots of sports and lots of scores to handle. In this case, I'm going to use quicksort. It's going to be the most efficient. And although we might have the worst case, I doubt that the scores are going to be sorted because there's just so many different kinds. But I'm also worried about in-memory sorting. So if I used merge sort, it might be a little too much for this because of our increased space complexity versus quicksort, which, if we remember, has better space complexity. And by the way, you might have your own answer for this. Maybe you thought that the sports scores on ESPN the inputs will be a little bit different. You can have your different types of answers. The idea here in an interview situation is to explain yourself. And if you know the principles, then the interviewer is going to say, oh, he or she knows what they're talking about. Number 4, massive database. So we can't fill all this data into memory to sort it. So we probably need to sort it externally, and let's say we need to sort through past years' user data. So it's a ton of data, and we need to sort it somehow, let's say, by some sort of a date. Well, based on the information that I got here, it sounds like I need to do something called merge sort, my favorite type of sorting. And the reason I would pick this is because, well, it sounds that we're not going to be sorting really in memory because the data is so big. But because the data is so big, I'm really worried about the performance. I don't want the worst case of quicksort of O n squared. I want to make sure that no matter what, I'm going to get O of n log n. What about the 5th one? There's an almost sorted Udemy review data that needs to update and add 2 new reviews. So we have a massive list of Udemy reviews. Let's say that you rated the course and this course that you're taking has 500 reviews and you and your friend just added 2 new reviews to this course. In this case, I'm going to use insertion sort. And why is that? Well, although this data might be huge and maybe I have a lot of reviews, I'm assuming that most of the previous data is already sorted. And all I'm doing is adding 2 new reviews to this data. Insertion sort for pre-ordered lists is going to work better than any other type of sorting. Number 6, temperature records for the past 50 years in Canada. Oh boy, what should we do with this one? And this is a little tricky. I would say that first, I would use something like Radix or counting sort. If the temperatures have no decimal places, if we're saying, it's minus 30 to, let's say, 40 degrees. That's an integer number between a small range. That might work well. But if I want to sort through data that also has maybe temperatures that are really accurate and have decimal places, which you can't do with Radix or counting sort, then I'm probably going to use quicksort, again, just so we can do some in-memory sorting and hopefully save on that space complexity. All right, last 2. Large username database needs to be sorted. Data is very, very random. All right, so we have a username database that needs to be sorted. I'm not really sure. I don't have enough information to make a decision here. Maybe I would use merge sort if we have enough memory and memory isn't too expensive on the machine. Or maybe I'll use quicksort if I'm not too worried about worst case and that the username database isn't that large. Maybe I'll just use quicksort just to save on that memory space. And then finally, number 8, you want to teach sorting for the first time? This was a little fun question. I said bubble sort, just so I can add bubble sort to this list and selection sort. All right, hopefully you had fun with these questions. Sorting algorithms, this is probably the funnest I can get it. Actually, no, I lied. The Hungarian dancing to sorting is the funnest you can have with sorting. But I hope you have a good idea of how to answer these questions when they come to the interview. I'll see you in the next video. Bye-bye. Welcome back. I wanted to have just a quick video to tell you about something interesting. And this depends on your language. But remember the sort method that we had in JavaScript? Or perhaps your language? I challenge you to figure out what sort of sorting algorithm it's using underneath the hood. Now, in most cases, it's either going to be quicksort or insertion sort and merge sort combined together. So go out and search what sorting algorithm your language uses. When it comes to JavaScript, there's actually no requirements to JavaScript as to which sorting algorithm to use. We have ECMAScript in JavaScript, which is the standard. Well, because the standard doesn't mention how this should be implemented, different browsers that have different JavaScript engines, Chrome has V8, Mozilla has its own engine, Safari its own engine, they all implement them differently. Well, last time I checked, in Mozilla, they use merge sort for sorting. And in Chrome, in the V8 engine, sort is implemented with quick sort and also insertion sort for the smaller arrays. I thought that was interesting. Anyway, I'll see you in the next video. Bye-bye. Another section done. And we covered sorting, specifically sorting algorithm in this section. Most of the time, when talking about sorting algorithms, we're going to be talking about O of n log n. We learned that there's a ton of sorting algorithms, and we covered the main ones that get used more often. If you're really excited about the topic and you find this interesting, then, well, good for you. You're one of few. I encourage you to search different sorting algorithms. But to review, quicksort you want to use when your average case performance matters more than the worst case performance. Because quicksort allows us to sort in O(n) log n, but in worst case, in O of n squared. Merge sort, on the other hand, is great because it's always O of n log n. It's also stable, which means that it always gives the same results in order if two items are the same. Although the space complexity is a little bit higher than quicksort, it's definitely a useful sort. We also talked about insertion sort, selection sort, and bubble sort. Those are fun when you're doing something quick and dirty and you want to just experiment around with sorting. But in real life, you're not going to use them. And most likely in real life, you're using the framework or languages or libraries sorting algorithm. Their advantage is that they're fairly easy to implement in code. And during the interview, you might say something like this in those rare cases that they ask you to implement a sorting algorithm. You'll say, well, because we have a time constraint, I'd like to use something naive and not efficient like bubble sort, which is slow in real life, instead of implementing something like merge sort, if it's okay with you, because we can assume that merge sort is something that we can implement with a library or fairly easily with documentation. Or you can say something like, we can just use merge sort to divide and conquer the code to make it more efficient. And this way, you show the interviewer that, yes, you can implement sorting like bubble sort, but you also know about things like merge sort to make it more efficient without having to actually implement it. So by the end of this all, I hope you now understand the trade-offs, where you can look at sorting algorithms and decide based on their speed, stability, and their readability, whether the input is already sorted or nearly sorted. How large is the input? You can make the right decision on sorting. I'll see you in the next one. Bye-bye.